Okay, so we are on, we're in 4.3. This is problem 6 on the homework. The vertical intercept should be old news by now, right? Vertical intercept means what? Y-intercept, which means you always make the other variable 0, so x equals 0, and that's easy. You can just plug in, right? That's easy peasy. You should be able to do that. If you can't, please rewind, watch the remaining part of the video or the previous videos. Now, for the horizontal intercept or x-intercept, that corresponds to zeros. What do I mean by that? Remember that if a certain number is a horizontal intercept, let's say x equals 3 is a horizontal intercept, just for sake of argument, then x minus 3 would be a factor. Okay, so that would mean x minus 3 is a factor. Okay, that's kind of the idea. So finding factors and x-intercepts is kind of the same task. Now, another issue is x equals 3 would be called a 0 of the function. The corresponding x-intercept would be the point 3 comma 0 would be the so-called x-intercept. Okay, so when we're talking about horizontal intercepts or x-intercepts, we're talking about the xy coordinates. When we talk about the 0, we only care about the x coordinate of that x-intercept. Okay, and then of course a 0 corresponds to a factor. X minus the 0, x minus the number that represents a 0, gives you a factor for the function. All right? So now let's go ahead and work this out. So how do I find those zeros? Vertical intercept we said is easy. Horizontal intercepts and zeros kind of go hand in hand. How do I find them? Well, we need to factor, okay? Because whatever makes a factor equal to 0 is your x-intercept. So you need to factor. Now in this case we got lucky because all three terms have a common factor. The greatest common factor in this case is x. We can factor an x out of all three terms. So I have f of x can be rewritten as x factored out. I've got a 2x squared plus 11x plus 15. Okay? Now, is that fully factored? No, because there's still powers. Can I go further? Yes, hopefully this will factor further. Now we can try factoring this by hand. The only way to make a 2x squared would be a 2x and an x. How do I make a 15? Either a 15 and a 1 or a 5 and a 3. Probably I'll go with a 5 and a 3. If I do plus 5 here and plus 3 here, let's see what happens if I, remember, to check a factorization, we kind of do a FOIL. So if I just FOIL these guys right here, just to check them, let's just do a FOIL on them, just to check the factorization. First times first is 2x squared. Outer times outer is 2x times 3 is 6x. Inner times inner is 5 times x or 5x. And then last times last is 15. 6x plus 5x are like terms, gives you 11x. So that is a correct factorization because when I FOIL out the factors, I get back to the original quadratic expression. So this is the correct factorization. Don't forget, though, that there's also an x out front because we pulled that out as our greatest common factor initially. So there's my factorization. There's no more powers left. When there's no powers left, you're fully factored. So what are your x-intercepts? Just set each factor equal to 0. Whenever a factor is 0, you get an x-intercept, okay? Or 0 of the function. So already solved. Right, so here are my, whoops, that should be a -3, sorry about that. Okay, so here are my zeros. In this case, I've got, if I go in ascending order, -3, then -5/2, then 0 are my zeros. What about the corresponding x-intercepts? Well, if the x is -3, the y is 0. That's why it's an x-intercept because the height is 0. -5/2 and 0. 0 and 0. Okay. What about the vertical intercept? That, again, we said that before. That should be easy. You should be able to get that right off the bat. Okay. All right. So let's go on. This one was actually pretty easy because we were able to easily get a GCF factored out. That made life a lot easier for us. Okay, so we're at, actually, I believe, problem 8 here from the homework, but let's just go ahead and work this through. First of all, what are the zeros? Well, I've got factors, right? So I've got a factor of negative 13t minus 12 is a factor of the function. Okay, so that's a factor. Now, how do I convert that factor into a 0? Whatever makes the factor become 0 will make the whole function become 0. So that's a 0 of the function. So if you set your factor equal to 0 and figure out what makes that true, that quantity will make the whole function become 0. Because if I plug in the value of t that causes this factor to become 0, 0 times anything is still 0, and so the whole value of the function would be 0. So anytime a factor becomes 0, that is a 0 of the entire function. Okay? So this is pretty easy to solve, right? Negative 13t is 12. So t is what? Negative 12/13 in this case. Okay. Now how about this factor here? What do we do with this guy? Again, set it equal to 0. Right, we can reduce that. Okay, so those are my zeros. My zeros are what? My zeros are negative 12/13 in this case, and 4/5. Now, what is this multiplicity idea? The multiplicity is the number of copies of the factor you have. So the multiplicity of the 12/13 is 2, because it occurs twice. There's really 2 of those. The multiplicity of the 10t minus 8 factor is 7, because there's 7 of those. So my multiplicities are 2 for the first factor, 7 for the second factor. Multiplicity just means how many copies of that factor are there. Okay? And there you go. That one's pretty easy. Pretty easy, I would say, right? Not too hard. Maybe just one hard? Not two? Too difficult? One difficult? All right, we'll just go with pretty easy. All right, let's go to the next problem. Okay, this is actually the next problem, problem number 9, and this concept was actually, these questions about how many x-intercepts or turning points, these are actually from, this was already covered in the previous section in 4.2. So you should watch that video if you're not sure about this. Okay, just a quick little blurb about it. If you get stuck on a question like this, just always remember your good old friend x squared. Remember your good old friend x squared? Your good old buddy? Okay, what's an x squared function look like? It look like this. Or it might look like this. It might touch the axis one time, like that. Or it might even go like this and touch the axis twice. So these would all be x squared type functions. Okay? How many, I guess I could have made those different colors, but I think it doesn't really matter. It's easier to visualize if they're different colors. Let's see, I'll go with kind of a red here. Okay. So, how many turning points does each of these have? They all have one turning point. The function turns around, goes from decreasing to increasing, or vice versa, in just one place. Turning point, turning point, turning point. Okay. So notice these are all x squared functions. So the degree is 2. Okay. Notice how many turning points you have. How many turning points? Turning point, turning point. You only have one turn. There's only one turning point for each of them. How many zeros are there, or x-intercepts? In this case, there are either no x-intercepts, or one x-intercept right there, or two x-intercepts. Okay, so you have, in this case, you can have up to one turning point and then up to 2 x-intercepts. Okay, notice the degree is 2. So that kind of just reminds you of what's going on. When you have a certain degree on your polynomial, the number of turning points is 1 less than the degree, and the number of x-intercepts can go right up to whatever the degree number is. It could be less, like in this case here, this is an x squared function, but only has one x-intercept. This has no x-intercepts. But this guy has 2 x-intercepts. Okay? You can go up to, get as many x-intercepts as your degree is in your function. So that should help you answer this question. Okay? All right, so let's go on. Okay, so in problem 10 here, again, we're talking about degrees versus turning points. So just remember your good old friend, the quadratic, right? Here's a parabola, degree 2, turning points is 1. One turning point right there, the vertex. Okay, so it looks like turning points is 1 less than the degree, or the degree is 1 higher than the turning points. Okay, how many turning points here? 1, 2, 3. A turning point is where the function goes from increasing to decreasing, or from decreasing to increasing. It changes direction. So I have 3 TPs. So what's my degree going to be? The smallest degree would be, I'll let you guys figure that out. Okay? All right, let's go to the next question. Okay, this is actually problem 12 on that homework. And I know it says graph it, but we don't even need to. If I FOIL this, and I don't actually need to do the full FOIL, just remember, if I multiply the first term times the first term times the first term here is 1x. I have a 1x, I've got a 1x and a 1x. If you just multiply first times first times first, you get the first term of the FOIL, of the FOILed result. 1 times 1 times 1 is 1, x to the third, plus lower degree terms. Things like x squareds and x's and numbers will come out, okay? But all I really need is that leading term to deduce the properties, okay? Odd degree. So what does that mean? Odd degree means ends in opposite directions. The ends go in opposite directions. Okay, so 1 up, 1 down. Okay, so I can rule this guy out. This guy's both going in the same direction, right? Gone. Psh. How about this guy? Same direction. Psh. Gone. Okay, do you have to say psh? It kind of helps a little bit. Yeah, you might want to. Okay, now, what about between these two guys? First of all, do we have the right x-intercepts? Where are my x-intercepts? My x-intercepts occur wherever the factor turns out to be 0. So if I set x plus 2 equal to 0, x plus 2 equals 0, I get x equals -2, so that's, I have to have an x-intercept at -2. I'm going to have an x-intercept here. If x plus 1 is 0, x equals -1. And then at if x minus 1 is 0, so at x equals 1. Okay, so I should have zeros at 1, -1, and -2. But it looks like they all do that. 1, -1, -2, 1, yep. I'd have to magnify this one a little bit to make sure, but actually this one might have the wrong zeros already. Okay, so it looks like it's going to be this one because of the zeros. But another way to tell is notice that the leading coefficient is positive, isn't it? Positive 1x squared, so my leading coefficient is positive. What does that tell you? If you don't know what that tells you, then you did not fully understand the previous videos. And that's bad. That means you did not understand them, which means you're not going to do well on the test on this material. So you need to rewatch those so that these become automatic. Okay? If the leading coefficient is positive, that tells you as you move to the right, because that leading coefficient tells you what happens as you move to the right. That means as we move to the right forever along the graph, the function goes up. So that's this case. Okay, now since the polynomial has an odd degree, the other side is going to go down. Okay, so that again tells me this is the right graph. Okay, the other guy has the wrong behavior here. It's going down to the right, which would be incorrect because we have a positive leading coefficient. Okay. All right, there we go. Easy peasy, right? Right. All right, let's keep going. Okay, this is problem 14. And it's we know that we want an equation for this function. We already know this x-intercept, right? This x-intercept is at 2. And when we have an x-intercept, we immediately know that x minus that x-intercept is a factor. Okay, what about this other guy? Well, looks like we have an x-intercept at -2. Oh, actually, -1, my bad. Sorry about that. -1. And so x minus that is going to be a factor. And of course, we can rewrite that factor how? X plus 1, right? Now here's the issue though. There's a difference in the behavior here. In this case, we're passing straight through. In this case, we're flattening out first and then going up again. Okay, when we pass straight through like a straight line, that means that the factor has degree 1 or multiplicity 1. Okay, because we're just passing straight through like a line, like the graph of x minus 2 would just be a straight line. In the neighborhood of this x-intercept, if you were to magnify it, this would almost look like a straight line. Okay, and so the power or multiplicity on this is a 1. Now what about over here? If I magnify this, this region, here's what it looks like if I magnify that. Okay, it kind of looks like this. It's kind of coming down, flattening out, crossing through, but sort of flattening out first. When you have that sort of behavior, that's x cubed behavior. If you look at the graph of x cubed, it kind of flattens out before it passes through the axis. Okay, so that means there's a degree or multiplicity 3 on this factor, or the corresponding factor. There's 3 of them there. Okay. The other kind of behavior that you'll get sometimes is if you have a bounce off. If I had a bounce off like this, let's say this was at x equals I don't know, -4. So this would mean that you'd have that your factor would be x plus 4, x minus the -4 is x plus 4 squared. Why squared? Because it looks like a parabola. When it looks like a parabola, that means the corresponding factor has a degree 2 or multiplicity 2. When it looks like a saddle like this, like you could sit on a kind of like a horse saddle or something, that kind of flattens out first and then goes back in this, like coming down, flattens, and then goes down some more. Okay, that's x cubed behavior. So in this case, my x-intercept was at -1, so we had x minus the -1 cubed, or x plus 1 cubed. Okay. So my function's going to be, in this case, my function's going to be x plus 1 cubed times the x minus 2 to the power, x minus 2 to the power 1, which we can just write as x minus 2. We don't need the power 1 on there. The next question is, do I have a plus 1 or a minus 1 on the outside? Is there a plus 1 here, or maybe a minus 1 as a number, as a multiplier? Well, the sign of the leading term tells us what happens as we move to the right. So as I move to the right along this function, I'm going upwards. If you go up to the right, that means you have a positive leading coefficient. If I were going down to the right, like this, I would have a -1 here, negative leading coefficient. Okay, so the behavior as you move to the right tells you, as we walk along the function to the right, tells you whether you have a positive or negative leading coefficient on your polynomial. Okay, so the behavior of the function near those x-intercepts tells you the degree or multiplicity on the factors. Multiplicity 3, multiplicity 1, okay? And then the what happens as you move to the right tells you the sign of the leading coefficient. Okay, so this would simply be x plus 1 cubed, x minus 2 in this case. Okay? And there you go. If it was moving downwards, if I give you a function that's moving downwards, kind of like this, then down to the right, you'd have a negative in the front instead of a positive. Okay? And there we go. Fun, right? Let's call it a yes.